allow me to talk here about the problems that I'm thinking about. And I think a better title will be on the rational and local motivic homotopy. So, one of the classical questions that we have in algebra and in topology is that if we can recover the information of, let's say, a finite abelian group from its rationalization, or for the p-completion of the finite abelian group. And naturally, so what we have is that we have this classically these arithmetic squares, where from the periodic information and extra maps in the rationals, we can recover the integer information. So this is a natural question to ask for abelian groups and for sure for homotopy groups. And then a question is, if we have a nice space, so from the rationalization or for the periodic completion, can we recover good enough information of the space? So then, so classically, also another important question is that, for example, we have examples of spaces when the cohomology rings they are isomorphic, but they don't have the same homotopy type. And it's important to also consider the multiplication that we can induce with the diagonal map, or the multiplication that we can induce when we take the singular complexes. So this question, it was classically studied in topology by Sullivan, and he used for the rational homotopy type, he used commutative differential Gradient algebras over the rationals, and he can recover the rational information of the homotopy groups when the spaces are nilpotent. And also Quillen used the category of differential graded coalgebras or the rationals up to, and the category of differential Lie algebras or the rationals, and some connectivity conditions. And he can recover again the homotopy type for simply connected spaces. Sullivan imposed some conditions of her finite dimension cohomology groups, rational cohomology groups. There is in the p-local part, Mandel has this work using infinity algebras, which is analogous to the work of Sullivan. And Gors also has a work using simplicial commutative coalgebras over a field, when he imposed the condition that K is a perfect field. So I'm going to talk more about this model of Gors in the motivic case. And I haven't told you what it's are rational equivalent. So when we have the homotopy category, we impose most equivalences, and we say that two spaces are weak equivalent if they induce an isomorphism in their rational homology groups or in the rational cohomology groups. And then we have an equivalence between singular homology or singular homology. So the question is, now we have, if we fix some notation, and we take F and K perfect fields, and we take the homotopy category of motivic spaces. So Vesna was talking about this during the workshop. And in this case, I'm going to choose a model. Essentially, most of my work was most of the things that I was doing was in the language of model categories. So then I take the category of simplicial preshifts over smoother schemes over F, and then I choose the injective model structure. Where the real equivalences are the quasi-isomorphisms and the configurations are the epimorphisms. So, and again, we play this game taking the Bosfield localization with respect to a dictionary topology and take the A1, the Bosfield localization, the A1 Bosfield localization. And the formal question is that we have the homotopy category, and we can define some rationalist, some localization for K another perfect field, whether or not there exists D and homotopy category of algebraic nature and F fully faithful functor. So the first question is what we are going to consider the analogous for the singular homology, the singular cohomology for these cases. So in this case, I'm going to work with the model of Gauss, and he used localization for singular homology. And then we have two natural candidates for the singular homology in the category of motives. And the first one is the A1 homology, defined by models. And so this is defined that we have a motivic space, and then this is a simplicial preshift. So then we take the free model, let's take K a perfect field, and then we take the motivic localization in dA F, and then we take the A1 homology of X with K coefficients is the homology of this chain complex. So this is a priori somehow naive homology theory for motivic spaces, but it's not at all naive as Morel shows. And one of the nicest things about this homology theory is that, for example, the A1 homology of GM smash N is related to the Milnor middle-beer K-theory shifts. And the second natural homology theory that actually what it's nicer somehow is Suslin homology. So this homology theory, so this definition, I think, to my understanding, brings the definition of transfers, which are important in the category of motives. So then this homology of a motivic space with k coefficients is equal to the homology of the complex of the simplicial set defining in this way. So yeah, I think I hear. Yeah, okay. So what we do is that so we consider the adding transfer functors to X, and then we take the homology group of this simplicial of this chain complex. What I'm saying with that is that we have the category of smooth schemes over K, and then we go to the category of corresponders over F, and then we go to the category of corresponders over F, where here the objects are also smooth schemes over F, and the morphisms are a little bit bigger. So the morphisms between X and Y is the free module or free vector space in this case, generated by all the subschemes, closed subschemes of X and Y, which are finite subjective. Over here. So I think I did it by choice. Yeah. So then I want the problems that I'm thinking about is to think about these two localization, this kind of naive localization and the localization with respect to Suslin homology shifts. So also one thing that I want to mention about this homology theory is that that the homology, the Suslin homology, of GM smash n is related to the linear K-theory shifts. And yeah. So now
sorry, I have to ask. Did you say you're formally inverting the affine lines and
sorry?
Did you say that you're formally inverting the affine lines and that?
Yes, yeah, okay. No, I didn't say that, but yes, sorry. I mean, how we do, so we have to apply the SUSL, sorry, yes, you're right. I'm taking this homology in the category of VM with K coefficient. And yes, you're right. Then what I have to do is to apply the Suslin complex to the added transfer math. Yeah, thank you. And yeah, so then this is a problem that I want to do. And then I want to give this approach to use a category of commutative coalgebras in order to try to study a localization with these two homology theories. So for the case of A1 homology, the things are easier because we don't have the presence of transfers. So all what we want is the following result. And we have that let K be algebraically closed. And then we have that the diagonal map induces a structure of coalgebra. So a structure of coalgebra in this initial object. And then also it turned out that when we take the localization and we identify more equivalence with the A1 homology, so there is a fully faithful contour induced by this diagonal map to the motivic category of the Mitzinevich and A1 localization of a category of simplicial commutative coalgebras over smooth schemes over F. So again, for this, so there exists let's denote this diagonal map as K delta. So there exists a fully faithful contour. So again, since the beginning, I started choosing a model structure for the category of motivic spaces. They started with injective category of motivic spaces because we want to use a model structure for simplicial coalgebras. The way to induce a model structure for here is that if we are in simplicial modules over K, in sheets of simplicial modules, then we right induce a model structure in the category of coalgebras by the forgetful. So we have the forgetful contour, and then we have the complete contour. So here we choose an injective model structure, and then we want that we equivalences here. So when we forget the coalgebra structure, we get quasi-isomorphisms, and the cofibration. When we forget, we want surjections for this model structure.
Sorry, can I ask when you write like modules, K
Vector
modules
spaces.
What do you mean?
Like presheets of simplicial or the simplicial vector spaces.
Oh, there's already presheets there. Okay.
Yeah, it's already and presheets level wise. And also this is important because it's very simple. The coalgebras that we get here, like everything is section wise. So the monoidal structure is section wise, and then the coalgebras are quite simple. So it's just section wise coalgebras. It also presheets of simplicial coalgebras. So then, since we don't have the presence of the category of transfers, we can translate completely the results of course in this case. It doesn't depend also, so here I choose this injective model structure, then we can induce a model structure here, and then we can consider any Bosfield optimization with respect to a collection of maps. Then we have a local model structure, and then again we induce a local model structure for coalgebras, which turned out to be just formally a Bosfield localization of the category of coalgebras. So then we have for free the results of Gauss. And one thing I want to mention is why the results of Gauss works for getting this fully faithful adjunction here. And the reason why this his results worked are because so we have a good understanding of the category of commutative coalgebras over a field. First of all, over a perfect field, and even better when it is algebraically closed. So these two conditions are important for that, and they are okay. So then, what we have is that so we can understand very well this category of coalgebras. The first thing that we have is that it's finitely generated. So every coalgebra over a field is a colimit of finite dimensional coalgebras. So also we can define simple coalgebras, simple subcoalgebras of a given C a coalgebra in the category, which are all the coalgebras which doesn't contain any proper subcoalgebra. Then we can define the irreducible components, which are the subcoalgebras which contains only one simple subcoalgebra. And then we can define some important part of a coalgebra, which is called the ethyl part of a coalgebra, which is the direct sum of both this C alpha simple subcoalgebras. So a result that we have about it is that so we have that the ethyl part of a coalgebra is an injection in a coalgebra, and actually this coalgebra is a direct sum of all its irreducible components, and it has so this injection is natural, and it has a natural split. So the fact that we have a natural splitting allows me to prove that allows us to prove that this is a fully faithful phantom. And one thing that is complicated, I think, in general for the category for a homotopy category of coalgebra is to find fiber replacements of the coalgebra, because in order to, so the counit of this map, the derivative counit of this map gives us a rationalization of the space. But then we have to find a fiber replacement for this, for an associated coalgebra, and it's difficult to find a proper fiber replacement in this category. So then,
yeah. Do you have a good description of what the A1 equivalence is and the Nisnevich equivalence is?
This I don't know, and I think so. Since the things are section wise and everything was formal, but then when I want to go to the Suslin homology localization, then I start to have complications because I don't have this nicer section wide description, and the things get more complicated because I don't have a good A1 fiber replacement for these coalgebras, for example. And yeah, so then I wanted to say that, and we can also say something about the case when K is not algebraically closed. So because also so far we're imposing that K is algebraically closed. Also, I haven't said the reason why we ask for this to be algebraically closed, and This is because when K is algebraically closed, so the right adjoint of this diagonal functor is the group-like functor, which is it's computed in the canonical way, in the most naive way, and are all the homomorphisms. So you have a coalgebra, the group-like part of the coalgebra are all the ones in coalgebras from K to C. When K is algebraically closed, so the coalgebra induced for this for K is given by the diagonal in Joseph point. So it's also a very simple structure of coalgebra there. And then we have that the coalgebra associated to the group-like part is actually isomorphic to the ethyl part of the coalgebra. But this is just in the case when we have that something is algebraically close. We can say a little bit more about the not algebraically part, and then
Classically, are the localizations
sorry.
are the localizations different, or even here of the motivic category? Let's say with respect to, I don't know, homology with respect to K or some finite extension of K. Are they different?
They are, and I mean, exactly the things that I'm stating are the same statements in topology. If we consider singular homology, so then we, I don't know, maybe I don't
So the left hand, the category you're trying to approximate is the same.
The category of simple coalgebras over a field.
No, sorry, I meant the other one, the local spaces, localization.
The localization is with respect to singular homology with K coefficients.
Let's say with FP or FP squared coefficients, it's the same, no?
Yes, exactly.
Okay, so you're trying just to, or even FP bar. So you're trying to approximate the same category. What have you lost if you just pass to the algebraic closure?
Okay. Yeah, for example, I think there are examples of no, I mean, maybe I don't understand your question. So, okay, let me state the theorem and then maybe. So now what we need, so let's assume that K is not algebraically closed. So what we need here in this case, okay, let me continue and then maybe I can answer your question better. So then what we need in the beginning is a category of G discrete motivic spaces. And so now we have the category of discrete motivic spaces. We again, so what we need is to take a G equal to the Galois group of K bar over K, and we take a category of simply Shelby shapes and the orbit category times smooth strings over F. And so then we have the topology given by codimension. So then we take the localization of the Nisnevis localization, then is the G Nisnevis localization, the positive localization of this category, and then the A1 localization for this category. This category also can be understood as the simplification sheets in the final dental side over K and smooth over F. And what we can get is that there exists a fully faithful functor from the homotopy category of the A1 localization of these motivic spaces to the homotopy category of simplification conjunctive coalgers over K. Spreadsheets again. So, and the fully faithful, how we define this fully faithful is that we consider a subgroup of G shows that the function is of finite order, and then we send this element, this constant simplicial shift here to the constant simplicial coalgebra associated to the bar, the fixed points of bar dual. So then the coalgebra structure that we have here is given by the multiplication of the field. And so then when for example when H is equal to G, we are taking K as a field, but now it's not this naive diagonal coalgebra structure, it's the dual of the multiplication for K. And so then so again the story repeats in this sense that we have a fully faithful functor from here, and I'm gonna denote this as this functor, and it has a right adjoint. And the right adjoint of this thing, what computes is the, so let's say that we have an element in this category, and then when we apply the right adjoint to C, let's call it this R of C n of G over 8 times U, it's equal to the etal part of Cn of U. So here the etal part is a bit more complicated when K is not algebraically closed. We have all the finite extensions of the field in the etal part. Actually, all the simple coalgebras are finite extensions of the field. And still, so with this functor we get localization of these discrete spaces, but we don't get the localization, and we're interested about to get the localization of motivic spaces. So we can embed this category with the trivial action, and then the group-like part, the homotopy fixed points of under this action, if the space was already local, gives us the localization of the space. So, I mean, all these are ideas in topology that they work well. I don't know if with this more or less I can answer your question.
I'm just wondering if, so I don't know, the way I understand the goal of, one goal of these kind of theorems is to give an algebraic description of a topological, of the localization of a topological category. And if you already have that description for, say, homology for K algebraically closed, why, and the right-hand side, this algebraic category is simpler when K is algebraically closed, and why do you
But do I bother for getting?
Yes.
Yes, I think. How was this story? I don't remember exactly the example, but I mean it's not
I mean, now you're approximating a more complicated category.
Yeah.
But so,
I mean, this category of coalgebras over an algebraically closed field is quite simple somehow. So we have more information when we don't consider the algebraically closure. And so in the middle, so like I think this theorem more or less can explain that we are asking for more structure, and we are not giving a naive coalgebra structure for this pattern, for this organization. And I think there are specific examples, but now I don't remember exactly how it works, where when the real homotopy type, there is a difference when you consider.
I think the answer is if you work with a field which is not algebraically closed, then the variety or the scheme that you are describing could be empty over the field. And when you go to the closure, then it's a completely different story. So take the sphere and with radius -1 over the areas. There are no points there, or you can even construct a model of P2 over some field which is empty, and then when you go to the closure, is what you expect it to be. And so the category over the finite field, over the field which is not perfect, or I mean, which is not algebraically closed, it's if you do it naively, then you are doing nothing.
I also can look for the other example. I have a more complete example about why we really care to keep not just the algebraically closed field. And
Different question.
yes,
The finite ATL site is about Galois cohomology. Do you see Galois cohomology in this function?
this set side is about what you meant. I don't know. Let me. Okay, so this is until the things until I work here are pretty formal somehow. Yes, you're right. When you see some ethyl cohomology in the sense that, for example, here if we take Eilenberg-MacLane spaces, when you take a 500 replacement of a space without this reduction, then the 500 replacement, it's the Eilenberg-MacLane space is not again an Eilenberg-MacLane space. And then in this 500 replacement you see the ethyl cohomology. And then this is a good question because so far here I need spaces without this reduction. And in general I want to recover this homotopy group. So here I say something wrong because if I take now K, so my idea is to recover the homotopy type of this. Now if I restrict to K to the rational numbers, then there I can say that the homotopy category of the rational, of the A1 rational homotopy type of spaces with the trivial action and then with the homotopy fixed points with these good spaces. So then for this case up to nice conditions I can recover the rational homotopy type. And these nice conditions are the natural conditions that we expect is to have nilpotent spaces. And in this case, we are asking for A1 nilpotent spaces. So we are working with the A1 homotopy groups, and then we are asking to these A1 homotopy groups to be A1 nilpotent. We have to give a proper definition about what it means to this A1 homotopy shifts to be nilpotent, but it can be possible. And also there is, last month, there was this work of Hopkins, Fassel, and Sock, when they work with this, with the specific examples of A1 nilpotent spaces, and they compute rationalizations of these A1 nilpotent spaces. So yeah, okay, this is a good reference that it's a good. I mean, it's a good localization of class of spaces. And now I want to go to tell about a bit of the problems that I'm having now. And so as I told you, I need to, in order to work, I need to be able to do homotopy in a category of coalgebras. And then I was introducing this Suslin homology with this presence of transfer, and the Suslin homology lives in the derived category, in the category of motives. So my natural category to think about is the category of precious with transfers, with K coefficients. And for these species with transfers, I have a monoidal structure. Given by a Day convolution product. And then until this monoidal structure, I can, let's denote that monoidal structure with transfers, I can consider the coalgebra objects. So I take the category of coalgebras, commutative coalgebras, with transfers. So here I need to give, to be able to give a co-free functor for this category of coalgebras with transfers, and I have the forgetful functor. So then I have several problems, because as I told you, one of the things that this allows to work is that we understand very well the category of coalgebras over a field. And this category is way more complicated, this category of coalgebras with transfers. So one of the first problems in order to be able to do homotopy, and let's think naively, and let's think that I can work in the simplicial category of commutative coalgebras with transfer. So one of the first things that I need is to have a presentability of the category. So I need to find a set of strong generators of this category. And for this part, I'm able to do that. I'm able to show that this category of coalgebras with transfer is presentable. I need to play a little bit with the cardinality of the ohms, giving X an element in the smooth schemes over F, and actually it works for a reasonable category. So I need to play with the cardinality of the ohms from X to X to Y with these elements in C. And I also need to play with the dimension, the dimension of the disjunct union, given F coalgebra with transfer. So also I need to play with the dimension of this vector space. X with all the X in C or in smooth schemes over F. And then playing with these two cardinalities, I'm able to prove the presentability of the category. Yeah, so what else I'm going to do? But then I have problems, and I have, as you mentioned, I don't have a good A1 fiber replacement or a Mies-Nevisch replacement for this category of coalgebras. Many of the things they work formally somehow. So so let's say that since I have this presentability, I can work naively with homotopy theory in this category. So the following question is that if I have the category of spaces, and then I have this category of, let's think for the moment, because I'm not sure that this is the category that I need, and this coalgebra with transfers. Okay. So the first question is, which one is the functor that I need to define here? And a priori, I think it's not naively induced by the diagonal functor. It has to be related, but it's not naively like that. And also, which one is this Rayleigh-John for that? one of the problems that I have is that when I'm considering this category of commutative coalgebras with transfers, I have this canonical maps. So from the Suslin complex applied to here, I have a canonical functor to adding transfers to the product. And we have a canonical functor from the product of the Suslin complex with transfers. Oh, sorry. So I have these canonical functors, but not something here that naturally gives me this algebra that I need. And I feel that it's not going to be that easy to find this appropriated fiber replacement for, well, this appropriated functor or this appropriated association for these coalgebras with transfers. And one of the things that these last days I learned that there are examples where so let's assume that F is a number field, and let's take sigma to invariance in the complex number. So I found out a paper from François that when he proves that there are smooth varieties over F, smooth algebraic varieties over F, conjugated varieties shows that they have a different cohomology algebra, or real cohomology algebra. So it's true that I'm working on dually, but they somehow should be equivalent. And I was reading about this, and they construct this example out of a product of elliptic curves, where they can find two smooth algebraic varieties where they have different real multiply. And I believe that the complications comes from the fact that this coalgebra with transfer is giving me more information of the base field, not just of the coefficient field that I have there. I think yikes. I still have time, but I think it's what I prepared.
Any questions?
On the rational side, do you see any sort of minimal model calculus?
Sorry?
On the rational side, do you see any sort of minimal model calculus?
Not exactly. I mean, but so I was saying that there is a nice work of Hawkins, Fossel, and Nauk, and they are working more in this part of the problem. Let's put it in some way, and taking so when you get a positive decomposition of the space, then you can easily keep rationalization of the Eilenberg-MacLane spaces, the A1 Eilenberg-MacLane spaces. So they have very nice examples from this part. I was trying more, or focusing more into getting these algebraic models somehow. And I mean, other nice thing that we can say about the rational part is that we know that the dA without transfers in the eta topology is equivalent to dm with rational coefficients. So somehow maybe this part of the transfer is not really needed for this rational part, but maybe for the peak part. And maybe another thing that I would like to mention is that other of the approaches that I was trying to do for this category of coalgers with transfers, it's one nice result that I got is for the eta topology, this monoidal structure with transfers behaves like a usual monoidal structure. So then, but I think there, in order to I mean, but that part will be for the eta topology. So then I'm trying to put, if I am able to put these things in order and to see if I can define a nice contour here. And that's all.